to be just 3 input NOR gains. So it had to have a fan of 3. So that was a constraint on the thing. I think that makes for a pretty good real-world design example. So we're going to move on from that. Today we're going to talk about another cool thing that will kind of throw a wrench in your design process. And that is a thing called gate propagation delay. Basically what that means is the digital stuff, although we draw it as if it happens instantaneously, doesn't actually happen instantaneously. When an input is applied to a logic gate, the output does not occur instantaneously. Now, there is some time in between when the input happens and when the output happens. So for example, we have just a simple inverter. We got X on one end, we got X prime on the output side, and we're going to draw a diagram called a timing diagram. And we're going to draw a lot of timing diagrams over the remainder of this course. And they'll come in various flavors and shapes and stuff like that. But here, the basic one is we plot a sort of a 2D axis. On the horizontal axis, we put time. On the vertical axis, we don't really put anything, but what we're going to do is we're going to note X, give it a place where 0 is, and a place where 1 is. And for our output signal, we'll call it X prime. We'll kind of do the same thing. We'll give it a place where 0 is. And we'll give it a place for 1. And so what happens is, the input starts at 0, right? We're sort of simulating what's going to happen. The input starts at 0. And if the input starts at 0, where does the output start at? Good, yeah, at 1, right? The output starts at 1. Those are the initial conditions of our system, right? Eventually we'll see circuit elements that aren't quite so cut and dry, but for an inverter it's pretty easy. You got 0 on the input, you're going to get 1 on the output. Now what happens is the input switches from 0 to 1. And up till now we've been drawing them as just like square waves. Or actually we haven't really been drawing them at all. But when we see them, they're square waves. But that's not actually what happens. What happens in real life? We flip the switch, what happens?
Not constant.
What's that?
It varies until
it varies, yeah. It's definitely not constant. What happens is it sort of slowly kind of ramps up, and then it ramps off. You get a thing that kind of looks like that. And there's some delay there that we'll just denote with epsilon. Like your math and physics classes, not epsilon dot, that's a different thing. Epsilon 1 just denotes a tiny, tiny value, right? So it's instant, like it's, might as well be instantaneous, right? You know, it happens in nanoseconds, or even picoseconds, which is like basically nothing. But if you're making a processor, or like a GPU that runs at 3 or 4 gigahertz, you know, a couple of nanoseconds is a long time, right? You gotta pay attention to that. So yeah, so what happens here is the output now, first off, doesn't even begin to respond until we've sort of capped off here, right? And then once it does that, it's going to do the opposite thing. It's going to sort of slowly kind of ramp off down to 0, right? And then if it stays that way, it'll stay that way forever. And it also has some delay time, we'll call it epsilon 2. And very often, these will be different, right? The sort of input delay time will actually be different than the output delay time. Sometimes the transition from 0 to 1 will be a different delay time than the transition from 1 to 0, depending on the circuit characteristics. You don't need to worry about that. It's sort of an interesting fact. Now the total time, from the time that we hit the switch, so we got our desired output, that's our propagation delay.
Mine are not directly under each other. Oh, wait, never mind.
What's that?
Never mind.
Why are they under each other?
I thought yours were like directly under each other. Mine weren't, but now I just looked at it closer and it's the same.
Yeah.
So,
So, yeah. So the total time from when we hit go until we get, till the output settles, till we get everything, right, is our propagation delay for that logic gate. Any questions about that conceptually?
so get harder than this?
No.
Alright, bad.
I think it's easier because after now you can sort of forget this little ramp part until you get to advanced digital design. If you do that. But, so we're going to do everything instantaneously. We're going to concern ourselves with this delay though, the input to output delay, the propagation delay.
Cool.
So let's do an example. So suppose, let's see, that we have a logic circuit. We're going to set it up like this. It's got an AND gate. That feeds into the OR gate. Yeah. We'll tie the output there to the AND gate. We'll take another input. We'll set that as 0. It will do an input A. And I'll stick a 1 there. We'll say that our output is F. And we'll say that each gate has a propagation delay of 20 nanoseconds. So each gate is going to delay by 20 nanoseconds. What we want to do is draw, we'll do it over here, the timing diagram for this circuit. Alright, so let's make it big. Alright, so that's time. We'll go ahead and put it in nanoseconds. And let's see. Let's do this. Let's have A appear. Was it 0? Let's have, what do I call it? It's G1, the output of the first gate, and then F. A.
How many are there going to be? 3?
Just 3, yeah.
Okay.
And then we'll put F down here on top. Just like that. Okay, so let's say, we'll break everything out in like 10 nanosecond steps. So let's say that life starts with everything A is equal to 0. Everything else is set, but A is 0. For these first 20 nanoseconds. What's the output of the gate going to be? The first gate, G1.
0.
going to be 0, right? Because we have 0 and 1, which means the output of the first gate is going to be 0. And the output of, actually I will bring it up just a little bit so we can see a little better. F. The output of F is also what? 0, right? 0 over 0 is 0. All right. Now at this point, it jumps up to 1. And let's say that it goes at least for 20 nanoseconds. Let's start there. All right. So, let's see. Actually, let's take it out. Let's go 40 nanoseconds. Otherwise, weird stuff will happen, right? So, yeah. So, what happens to gate 1? So, A goes to 1. So, G1 goes from 0 to 1, right? But it's got the delay. So, it's actually not going to go to 1 until when? Until 40 nanoseconds, right? All gates have a delay of 20 nanoseconds, which means that as soon as the input signal changes, it's still going to take 20 nanoseconds for G1 to click over. Right? And it's at least going to stay right there. In fact, we'll do this. We'll bring it down at 60 nanoseconds. We'll say it goes back to 0, and it stays at 0 forever. So here, when A goes back to 0, how's that going to affect G1? Kind of do them all in stages.
It goes back to 0, 20 nanoseconds later.
Yeah, so it goes back to 0, 20 nanoseconds later, right? Bless you. So there it goes back to 0, and it will stay 0 forever. Right? Simulation's over.
And that's 80.
That would be at 80 nanoseconds. Now let's talk about our output F. So we had 0 and 0. When A and G1 are both 1, right, it's going to be, what is F going to be equal to? 1. So the change doesn't occur until, well, the input conditions don't even exist until here at 40 nanoseconds, right? Which means it's going to take 20 nanoseconds for F to click over. And then what happens? A goes back to 0, but it takes 20 nanoseconds for G1 to go back to 0. So we have this instance where here A is equal to 0, excuse me. Well, yeah, G1 is still equal to 1, right? Which means our output F is going to stay 1, at least to that point, and then it goes to 0. So we have 0 and 0 at our OR gate. So that means it's going to take another 20 nanoseconds for F to go back to 0. And well, we done. And then it stays 0. So there's a couple interesting observations we can make here, right? First is that, we can see how the logic structure sort of settles out, but also we can see how long did it take for, when we changed A, for that output to appear here on F.
40.
Yeah, it took 40 nanoseconds. So there's like a maximum for circuit propagation delay time of 40 nanoseconds from the time we hit go until we saw the result on our output. So those propagation delays stack up as we add more and more circuits to the system. Any questions about that?
Nope.
Yeah. So that's just there. You just need to be able to sort of look at the logic circuit, know what the propagation delay are, sort of draw out your inputs, and then draw out your corresponding outputs for all your different gates based on the timing delays. Now this could lead to an interesting problem for a circuit that's a little bit more sophisticated than this. What can happen? do a more complex example. All right, let's say that we've got an input V. Which feeds into an inverter. Because here we'll actually draw the inverter. Then it goes into an AND gate. With the output of the inverter, so B prime. And input A. And there's another AND gate. Which takes B. Another input C. And they feed into an output F through an OR gate. So here's a question: how many levels is this circuit?
3.
Gotcha.
2.
2, right?
No.
Why is it 2?
Because
Don't count the
where
inverter.
don't count.
Yeah, except for now when they do count because we're talking about time. Yeah, so this is still technically a 2-level AND OR circuit. Alright, so a couple of the details we need to jot down. We'll say that A and C are both equal to 1, and every gate has a propagation delay equal to 10 nanoseconds. All right. So that, and then we're going to have, we're just going to change B, so we'll have B, we'll have the output of, we'll call this, I'll just call it A, B prime, right? We'll call this one BC. A for A, B prime, put it there. BC, put it there. And I'll leave it there. And then final level output F, right there. Okay. So we've got T in nanoseconds. We're going to use 10 steps for our horizontal axis. And so here's what happens. We're going to go. B is going to stay 0 for about 30 nanoseconds. Then it's going to go to 1. Oh, I lied. Got totally backwards. Here is B is going to be at 1, and then it's going to go to 0 at 30 nanoseconds. And then it's actually just going to stay at 0 forever. So this is the transition that we care about. A and C are both equal to 1. B is going to switch from 1 to 0, and then stay there forever. So when B is equal to 1, what is the initial state of our logic gate A, B prime? 0, right? Since we got B is 1, B prime is equal to 0, 0 and 1 is 0. So A, B prime is going to stay 0 until that point. And then it's going to switch over to what? To 1. But not until 40 nanoseconds, right?
Why does your line go under AB?
What?
Like this? Oh, it is, wait,
What are you talking about?
sorry. So AB, you have a little dash. Where's another dash under?
What is whatever dash? You about this? Yeah. It's because that's a smudge on the chalkboard. So. You could have think it was the 1. Yeah. All right. So yeah, so AB prime is going to go to 1, but it's going to wait 10 nanoseconds. All right, it's not going to click over until 40 nanoseconds. And then it's going to go to 1, and it's going to stay there forever, right?
Don't you have to calculate propagation delay of the inverter as well?
Oh my goodness, you're absolutely right. So what does that mean?
Takes another 10
Takes another 10 nanoseconds, right? Because we should draw on B prime up here. Alright, so that means it's going to take how long for AB prime to switch over?
50.
Yeah, it's not going to be until 50, right? So it's going to take 20 nanoseconds. Because we got to account for the 10 nanosecond delay in the inverter. Alright, then it flips over to 1. And continues on. Alright, now what about BC? So it started where?
1.
So it started at, so C was equal to 1, B was equal to 1, right? So it started as 1. Oh, all right, I'm glad you said that, because this demo kind of hinges on the inverse. Okay. So then B went to 0, and so BC is going to go to where?
0.
It's going to go to 0, but it's going to take 10 nanoseconds to get there, right? Because it's not dependent on the inverter.
Nope.
So it's going to take 10, and it's going to switch over. And it's going to stay there forever. So now let's talk about F. So we started with what? 1 and 0 on F, right? Which means F is equal to 1 coming out of the gate. Now its inputs don't start until, or nothing really happens until BC goes to 0, right? And when BC goes to 0,
Takes 10 seconds.
what happens to F?
Goes to 0.
Yeah, F is going to go to 0, right? Because we've got 0 and 0 here. Obviously, it's going to delay 10 nanoseconds.
So it's 50.
So at 50, it's going to click over and go to 0. But what also happened at 50?
AB prime goes to 1.
Was that? Yeah, AB prime went to 1, which means what for F?
It goes back to 1.
Which means F is going to go back to 1, but
It takes 10 nanoseconds.
it's got to wait. It's 10 nanoseconds.
Oh.
And then it goes back to 1. And it stays there forever. Right? So if we were to sit here and make the truth table for this circuit, well, first off, let's say if it was, so F is a function of what? A, B, and C. And is equal to what? A and B prime. Or B and C. Right, we already have A and C is equal to 1, and we set B equal to 0. All right, so that would be 1 and 1, right? Or 0 and 1, right? So I guess that's 1. What I'm saying is, so for the input combination on the truth table, right, we should have gotten a 1 on F, which is what we got. But what happened along the way?
It went to 0.
Let's do it first.
This happened. Right? It stayed at 0. Well, actually, we could even take a step further. Before we had that, when we had B equal to 1, we still have 1, right? So this transition in inputs should have caused no transition in the output. But because of the timing delays, we had this weird moment where the output clicked to 0, right? Now, it's not hard to see that that can cause all kinds of problems, right? Because what is F hooked up to? And what is it going to do when it sees a 0 sort of momentarily show up on its input, right? This is what we call a logic hazard. when, because of the way that the sort of timing is set up, the way propagation delays play out, a circuit can momentarily give outputs that are not what you intended.
So F should never be going to 0.
Yeah, by all of the rules that we've talked about so far in this class, when we set our inputs the way they were, F should have stayed at 0. Or excuse me, should have stayed at 1. Right, the entire way through. But because of sort of the realities of building the stuff, we get these moments where these logic hazards can occur.
So can that happen but the opposite way? Can I
Yeah,
go off to
that's-
1, go back to 0?
Absolutely. There's a whole sort of encyclopedia of logic hazards. There's all kinds of different things that can go wrong. So, but there are a few that we care about, or the sort of few that I'm going to choose to ask you to care about are roughly grouped into 2 categories. There are static and dynamic hazards. So, actually, can I just erase this board?
Yeah.
Okay. So a static hazard is a logic hazard which occurs only once during a transition. Right? This is an example of a static logic hazard, right? The transition happened, and we only had one instance of a thing going wrong. We went to 0 and came back, right? So, the terminology is, if it's at 1, and it momentarily drops to 0 and goes back to 1, we refer to that as a static 1 hazard. Right, it should be 1, and it jumped away from 1. On the flip side, you can have static 0 hazards, where it's at 0, and it momentarily jumps to 1, and then it goes back to 0. This is a static 0 hazard. Right? 0. So the way to remember it is, whatever the thing it should stay as, should be a static 1 hazard, or if it should be at 0, it should stay at 0, it should be static 0. Rather than Achilles, he tricks over to 1. A dynamic hazard, we typically don't label as like a dynamic 1 hazard or a dynamic 0 hazard, but a dynamic hazard is a hazard which has a bunch of different weird things, right? So maybe it's at 1 and then it drops to 0, then it goes back to 1, and it drops back down to 0, and then stays at 1, right? This would be an example of a dynamic hazard, where the hazard itself occurs more than once during the transition. I almost didn't take the mask down. All right, any questions about that? Okay. So, how do we detect logic hazards? Turns out, with K-maps, it's actually really easy to detect logic hazards. So adjacent groups on a K-map indicate presence of a logic hazard. So, well, let's do the one we just did, right? So f is equal to, bless you, a function of a, b, and c was equal to what, a and b prime, or b and c. So what we've got to do is do the reverse engineered K-map thing. So we're going to plot this guy on a K-map. So let's see, we've got A over here, B and C, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. All right, so where's A and B prime going to go?
What again?
5 and 6.
A and B prime, yeah.
5 and 6.
So 5 and 6. What's this one? 4.
Oh, 4 and 6, yeah.
That's going to be 4.
24 and 5.
5, right? So we have a group there. And what about B and C?
2 and 7.
What's that?
2 and 7.
2 and 7.
Green stuff.
3 and 7.
Oh yeah, I forgot about that.
Right, like that. So what you do is you got on your K-map, and now we can see the logic hazard. Adjacent groups on the K-map indicate the presence of a logic hazard, which means that there is a logic hazard between those two groups. Now let's see, what is this cell? This is 1, 0, 1. So we have a logic hazard. And a lot of times we'll have more than one at the transition point between 1, 0, 1 and yeah, 1, 1, 1, right? So that's 1, 0, 1, that's 1, 1, 1. So when A and C are both equal to 1, and when B toggles between 0 and 1, a logic hazard will occur, which is exactly what we saw, right? We say A is equal to 1, we switch B from 1 to 0. Sure enough, the logic hazard existed, right? Now, when we went from what, 1 to 0, and it stayed at 1, and went to 0, and then came back to 1, what kind of hazard is that?
Static 1.
Status 1, right? Good. Yeah. So when you're going to look for your logic hazards, you look at the K-map and you say, yeah. So how do we get rid of it? How do we eliminate? How do we redesign our circuit to no longer have a logic hazard? Turns out, what do you got?
I was gonna guess, did you like group the things differently, group the ones differently?
Well, you could group the. You
Well, not in this
could
case.
group it differently, right? So here you can't really do anything different. You did it correctly. Well, what you have to do is you have to now link the terms together. You got to do the thing that I told you never to do, which is actually do include the consensus term.
Wait, what do you told us that?
What's that?
What did you tell us that? I don't remember.
Right, we talked about, so what is, all right, well, let's take a look at it.
Could you also try to group the circuit by the zeros instead of the ones?
Yes, that could, you're absolutely right, but that would lead to a totally different set of logic hazards, right? So if we did the other way around and did the or and, we would have 0, 0, 0, 0, which would be adjacent here. So we'd still have a very similar logic hazard.
Oh, it's good.
what if it was in a different situation where it would be is it possible to have a logic hazard in one but not in the other? Like if you switch between the
Yeah,
points?
absolutely, yeah. It all depends on just what the function is and how the K-map shakes out. All different things can happen. So, but if we look here at just the function, right, x function ABC, and originally it was A, B prime, or BC. Now, if I go ahead and group these two terms, what's going to happen? What am I going to get? I'm going to get A and C, right? So we get 4 A and C. What's the deal with A and C? Right, it's the consensus term between B prime and B. A and C is the consensus term, right? So that's why I said, when we talked about K-maps the first time, I said, like you never, once you've already accounted for something, you never like link groups together because that just gives you a consensus term, right? Which leads to an unoptimized solution. But consensus term does what for you now? It protects you from logic hazards, right? Even though it's redundant, it can cover up that place in the sort of shakedown and prevent these logic hazards from happening.
So we should always watch out for consensus terms unless you're not asking for it. I mean, unless you're asking.
So, I mean, this is where you kind of, it gets a little philosophical, right? Right? Yes, adding the consensus term will give you an unoptimized design, right? And we've already kind of had to deal with that. We had to deal with fan-in and give us a design that was slightly unoptimized because we had a fan-in constraint. Well, here we have a logic hazard, and we got to make the decision, like, well, do we cover it up with the consensus term? Or do we add a whole other logic gate for the purpose of preventing that logic hazard? And what does the answer usually revolve around?
Money.
What's that?
Money.
Yeah, actually it revolves around money. But the conversation is going to revolve around, well, what will happen if that, logic hazard occurs, right? And if the answer to that is, an extra bit, the clock, it'll take an extra clock cycle or something to get the calculation that you want, or, something simple happens, it's not a big deal, right? But if this logic hazard is, the missile will explode while it's still attached to the airplane, then you want to add the consensus term, right? That's what I'm saying. Like then you're gonna sort of do the risk versus, yeah.
Okay.
What is the severity of the logic hazard? If the logic hazard occurs, what will happen then? Is that bad? Should we deal with it? Is that worth adding a logic gate, right? It becomes sort of a more philosophical, ethical discussion. But that's the gist, yeah. So we would redesign the circuit then. I think I just left it, right?
If the logic hazard happens over a don't care, can you just leave it in?
What's that? If the logic happens, if the logic hazard happens across a don't care, like for example, if let's say like this was a don't care instead of the one, is that kind of what you're getting at?
Yes.
Yeah, right? So then it actually might be, I mean, you're still not going to like save a bunch in optimization. So it might be better than to do that and have that term by itself instead of having that. But you're still going to, this is going to add another gate input, right? Which is a whole different thing, but that might be a better solution, right? Yeah.
For the purpose of this class, would we ever want to do that on a question?
Good question.
Yeah, it gives you the more optimized solution.
But would we get it wrong? Did we do either or? Or just more optimized solution? So it's like,
Well, the question says give us the optimized solution, and that's an optimized solution, yeah.
Does the optimized solution take the logic hazard into account?
I'm a little uncomfortable with the question because the question is, what thing do I need to do in order to get like a good grade, right?
yeah.
Which one is more important on your test? Because it's got to be one of them.
Well, that's what I'm saying, but it's not that simple, right? And I hate that. I mean, I'm going to pick on you, right? You're a fantastic student, so I don't take this personally. But yeah, I hate that question, right? Because it shouldn't be about like, well, what is going to mean? I mean, that's up to Max. You shouldn't talk to me about that. It's talk about what is Max going to count right or wrong, right? But it's like here, this is a sacred space, man, where we're talking about ideas. So the question is like, well, is it going to give you an optimized solution? Is the aircraft going to explode? Is it going to crash into the side of Mars? Like that's what I want you to worry about right now, right? The question should be specific enough to tell you what you need to know, right?
Okay.
And if the question says give us an optimized solution that's free of logic hazards, and this result gives you the optimized solution that's free of logic hazards, that's the one you should go with. Yeah.
Okay, makes sense.
Yeah. I'm not worried about what's, the right answer. Because again, I'm not trying to like trick you. Like this, like all students have this like weird idea in their head that like I'm trying to like, the professors are playing like weird mind games to like, we gotta do it just like a certain specific way. If I want you to do it in a specific way, I'll ask you to do it in a specific way. Does that make sense? I am never trying to like trick you into making a mistake. Does that make sense?
Yeah.
Cool. If you give a good answer, if you give a good design and you can back up your design and back up the reasons why you made the design, you're gonna get 100 from me, okay?
Okay.
Alright. So, let's say, so we're gonna have, nah, we don't have much time. Let's finish drawing this up, which I still have that time diagram. So yeah, so what we do is redesign the circuit. Maybe we can catch in the last 4 minutes here what happened. So we had what? We had A and B prime. We had B and C, and then what did we add? We had an AND gate for A and C, right? And yeah. Okay, so let's go fast. Can I erase this?
Yeah.
All right. Okay, so let's see. Now I'm definitely making a mistake. So A and B stay the same. We still got 1, so we got B. We got A and B prime. We got B and C. We got A and C now. And we got F. Hanging out there at the bottom. Okay. So let's see. B was what? B was 1. And then at this point in time, B went to 0, right? And stay there forever. A and B prime was at 0, right? No. Yes, it was at 0. It had to wait for the delay. So it went another unit here. So what we call 2 ticks. Then it went to 1 and stayed there forever. B and C was at 0 until it went to 0. So then it went to 0, right? And it stayed there forever.
Wasn't at 0?
What's that? No, because B was at 1 and C was at 1.
Okay.
Yeah. So then delay. So that should have been 10 nanoseconds after the fact. Now A and C is just 1, right? We just stayed at 1 forever. Which means what for F? We didn't even need to draw the rest of it. Because if A and C is 1, and for A equals 1 and C equals 1, F is going to be equal to what?
1.
F is going to be equal to 1 forever. And all this other changing has no impact at all on F. F is going to stay at 1. And so we never get that hazard, right? The switch from one input combination to the other should have been 1 to 1. Adding the consensus term removes the logic hazard and keeps it at 1. So by building consensus terms back into the circuits, you prevent the logic hazards happening. All right. Any other questions about that? Cool. All right. Well, we'll pick up with this on Monday. Enjoy your weekend. Thank you. Be safe and all that. See you guys on Monday. Thank you.
So 1, wouldn't we just make that 1 and a constant instead of a function?
No, because we're only, in this example, we're only concerned with that input combination, right? So there might be cases when A and C aren't equal to 1. So we don't want to change the circuit. We're just concerned about the logic hazard at that particular, for that particular input transition. Does that make sense?
Well, what I was going to say is, like, if we know for a fact that A and C will always be 1 regardless of whatever the previous states are, would we just reduce the entire thing down to just f equals 1?
Yes, if that were the case. But that was not, yeah. But that's not what happened here. Here it was, you can imagine a truth table with all the values of A, B, and C. And we were just focused on A equals 1, C equals 1, and then we transitioned B from 1 to 0. So we were kind of zoomed in on just one particular input combination. Does that make sense?
Yeah, I just wanted to make sure because I realized that was just a straight line, so we could, if we, in this scenario, since you said that A and C were equal to 1,
Yeah.
and that B was only one default, that I wanted to make sure that we'd be able to just simplify the entire expression to 1.
Yeah, so A and C were set equal to 1 for the sort of purposes of the timing diagram demonstration. The circuit isn't designed around the idea of A and C being equal to 1.
Okay.
Cool? All right. Thanks, sir. All right, thanks, guys. All right, what's up?
I had a simple question about the whole